Okay, welcome to lesson 7.5. We're going to talk about scalar and vector projections in this lesson. And if you've taken physics before, you've probably talked about projections in the context of like work being done. We're going to look at that in a future lesson as well. But here we're looking at the math behind projections. So a projection of A onto B is obtained by putting the vectors tail to tail at the origin and then dropping a line from the head of A perpendicular to B. So we're going to look at what does that even look like in a picture. And one of the ways that you can think about projections, if I'm projecting A onto B, what I'm looking for is like the shadow of A on B is another way to think of projection. So here's a couple of pictures of sometimes what projection might look like. I have this vector A here and a vector B along the bottom. The vector B is actually in blue underneath that red bit there. And if I'm projecting A onto B, then I'll drop from the head of A, I drop perpendicular down towards B, so it makes a 90-degree angle with B. And then the projection is this red piece here. And it can either be a scalar projection where I'm just looking at what's the length of this red piece, or it can be a vector projection, at which case we would put the head at the point N here on the end. So if I was looking for a vector projection, I would add a head to this vector. Now that's one way that that could look. Another way that it could look is maybe there's an obtuse angle between A and B, in which case when I drop perpendicular to vector B, I'm dropping down, I'm still going straight down, and the projection is actually on the opposite side of B, so it's not on top of B anymore. That's okay. And again, I could be looking at the length of this, we would call that the scalar projection. Or I could be looking at this as a vector, in which case, again, I would put the arrow over here. It's kind of like underneath the head of A would be the head of the vector projection. And then a third case that we might look at is what happens when there's a 90-degree angle between vector A and vector B. Again, this would be vector A and this would be vector B. Now when I drop down to find my shadow, it's actually right here, and the corner, the origin corner, is actually equal to that point N, and so here the scalar projection would be 0 and the vector projection would be the 0 vector. Another possible option is similar to this first one here. I could have my vector A and my vector B could be shorter than the head of vector A, in which case when I drop down, I would just be thinking about extending this line out, and then when I do the drop down, I'm going to end up with this vector here, and here my vector projection vector is actually longer than vector B, and that's okay as well. And so here, just a couple of labels. This would be A, B was this little short guy, and we are calling this corner N here. Okay, now all of these pictures that we've drawn here, we've drawn them as if B is on a horizontal, but that's not necessarily true. All of these pictures are true here as well. If I'm projecting A onto B, I'm just dropping down to B at a 90-degree angle. B doesn't have to be horizontal. Like I could be even, I could be projecting up as well, right? So here my vector B is above my vector A and I'm projecting up onto it, or it could be a vertical situation. So we draw it most of the time with vector B on a horizontal, but that's not necessarily true. And remember too, in 3 dimensions, I could be rotating this image out of the page towards you as well. All right. So we're going to talk about scalar projection first. So how do we find the length of these lines underneath, or the length of the shadow, you could think of it as. For the notation here, we're going to be using the absolute value bars or the magnitude bars to show that I'm just finding the scalar projection. And then it's important, the order of these letters here, A and B. If I'm projecting A onto B, it's B is like where I'm going to drop the shadow is going to be in line with B. So B is in the base here, and I'm projecting A onto B in the base. And to find the scalar projection, I would do the dot product, A dot B, and then divide that by the magnitude of vector B. And another way for me to write that, if I think about what I know about the dot product, remember that the dot product so if I were to sub that into this numerator here, the magnitudes of b would cancel, and I would just be left with the magnitude of a times the cosine of the angle, which makes sense here, right? The magnitude of vector a is really what's deciding my the magnitude of this shadow here. Okay, so we've got two examples here, or we've got an example here. We're going to find the scalar projection of A onto B, and then in part B, we're going to find the projection of B onto A. What we want to know is, does it matter what order I do this in? And so we'll start with A onto B. So we're going to find it is just scalar, so I've got my magnitude bars. We're projecting A onto B, so B is in the base, A up here. And so it matters, again, the order here, if B is in the base, that I'm dividing by the magnitude of B. So I'm going to do A dot B over the magnitude of B. I know that to find the dot product of two vectors in component form, I just multiply the matching components together. So I'm going to have -1 times -2. And then I add, multiplying the y values together, I get 12. And then I add, multiplying the z values together, I get -5. And then in the denominator, find the magnitude of vector b. Since vector b is attached to the origin at the tail, all I have to do is square each of the individual components. If it wasn't attached to the origin at the tail, don't forget that to find the magnitude, you'd have to subtract the values of the other point. Oops, plus. And so I can simplify in the numerator here, 14 minus 5, that gives me 9. And in the denominator, I end up here with the square root of 4 plus 16 plus 1, that's 21. Okay, so I'm not going to change that into a decimal. I'm happy there. I'm going to now move over, and I want to see, is it the same if I switch the order? So now I'm projecting B onto A. So that means that I'm doing the dot product, and I'm dividing by the magnitude of vector A. So the dot product is going to be the same in either order. So this is the same as the dot product of A and B, but in the denominator, I'm going to take the square root of the A coordinates or components squared. And so we already know the dot product of A and B. It's over here, it's the number 9. And then in the denominator, I get the square root of 1 plus 9 plus 25. And I see here that these are not the same, so that tells me that order matters. And you can imagine that as well with these pictures here. If I were to, like for instance, in this first typed example here, when I projected down, I would project the other way to find the projection of B onto A. I'm going to drop until I get a 90-degree angle over here, and you can see that the magnitude of this resulting vector is different than the magnitude of the other shadow, right? Depends which order I go in. Okay, so next we're going to talk about the direction angles, and sometimes they call them the direction cosines, between a vector and the x, y, and z axes. So they're calling them the direction angles because it's telling me the direction along the axes. So to find these direction angles, I'm going to remember that I can reorganize my dot product formula into this format here. And then what I'm going to do to find the angle along the x-axis is I'm going to use the x-axis standard unit vector. So that would be the 1, 0, and 0. And then if I was on the y-axis, I'll use the standard unit vector. along there. And then of course the same for the z-axis. I'll use the k unit vector. All right, oops, this guy's moved. All right, we're going to find the direction angles for this particular example here of this A vector. So this is my A vector from example 1, and what I'm just going to recall from example 1 is that the magnitude of vector A was equal to root 35. I know that that's going to come up here in my formula. So for the x-axis, I'm going to find the direction angle. I'm going to be using this formula here. And you're going to have to use a different symbol for along the different axes. So actually, instead of theta, I'm going to use alpha for the first one. That's what your textbook does for the x-axis, but it doesn't really matter as long as you have a different variable. And we're going to know that here the cosine of the angle is going to be the dot product divided by the magnitudes. And then I'm just going to sub in what I know. Now for the x-axis, I'm using the b vector as vector I. And so you could even write that in here if you'd prefer, like you could make these i's. And, or you can write it up here. So the first thing I'm going to do is the dot product here. So -1 times 1 plus 3 times 0 plus 5 times 0 over the magnitude of vector A, which we said was root 35, times the magnitude of vector B, which is vector I, and we know that the magnitude of the unit vector is 1, or root 1, same thing. And so here I get cosine, or sorry, I get alpha is cos inverse of -1 over 35, root 35. Type that into my calculator and I get about 99.7 degrees. All right, so now we'll just repeat the process. Along the y-axis, we're going to use b is the j vector. Again, using a different symbol, so I'm going to use beta. I'm going to dot these two vectors and then divide by the magnitudes. And so this time I'm going to be multiplying times the j vector. So I'm going to get 0 plus 3 plus 0. And again, I'm going to get root 35 times the magnitude of vector b, which is just 1. And then we'll rearrange and solve. For beta. And on my calculator, so I'm just typing this in. Make sure, again, you're practicing with your calculator that you can type that in and get the right answer. And then last one along the z-axis. So this time when I do the dot product, I'm dotting vector A with vector k over here. So I'm going to get 0 plus 0 plus 5. And so this time when I isolate for the angle, I get 5 over root 35. And when I type that into my calculator, I get about 32.3 degrees. All right, so that was all scalar projection type of stuff. Next, we're going to be talking about vector projections. So when I want the vector projection, we're going to kind of build up to the formula, thinking about, well, how will I find the vector projection? This is the notation here for the vector projection. And what this first line is saying is the vector projection is equal to the scalar projection multiplied by a unit vector in the direction of vector B, right? Because I want to know the length, this is like the length of the shadow, but then put it in the direction of vector B. So how do I find a unit vector in the direction of vector B? You might remember that to find a unit vector, I do 1 over the magnitude of a vector times itself. And I can simplify this by just saying it's the vector divided by its magnitude. And so that's what we have here. A unit vector in the direction of vector B is vector B divided by its magnitude. And I know that scalar projection, we came up with this formula on the first page, is the dot product divided by the magnitude of the vector I'm projecting onto. So this is just in words on the first line, same thing on the second line. And now we're going to try to simplify the algebra here. So just multiplying the two denominators together, we would get the magnitude of vector b squared. Or remember that when I have the magnitude squared, that's the same as dotting a vector with itself. And so you'll see both of these bottom formulas being used. I would say that they're both pretty useful, depending on the question. So usually, I would put a box around that. And this one's also useful. And so those are the two versions that you would want to know. All right, in example 3, we're going to find the vector projection of A onto B. And so this time I'm finding the vector projection. I actually want a vector as my answer, not just a number. So I'm going to be using one of these two formulas here. And I kind of see these as equivalent, whether I'm doing B dot with itself or finding the magnitude squared. It's the same idea. So we're going A onto B. So B is in the base. I'm going to use the first one. It doesn't matter that you could use the second one. And I'm going to talk about what the difference might be here. So in the first, in the numerator here, dotting the two vectors together, I just multiply the x's together, add, multiply the y's together, add, multiply the z's together. And then in the denominator, I'm thinking about this as a magnitude being squared. So I'm thinking about the square root, and then I'm squaring and adding each of these components. But then I'm taking that and I'm squaring the magnitude. So there's another squaring on the outside here. And then I would multiply by vector b. Now, the other way to think about this, if I don't want to think about it as the magnitude squared, is I could be thinking about the dot product of vector b. So I'm just going to do that off to the side to show that it is exactly the same. When I dot a vector with another vector, I multiply the x's together. So I would get -1 times -1. And then I multiply the y's together. And then I multiply the z's together. And notice here that I have a square root and a squaring that are going to cancel, and I end up with the exact same thing, whether I'm thinking about it as a dot product or a magnitude squared. Okay, so that's just an aside. You wouldn't normally include both. In the numerator, this simplifies to -23, and in the denominator, we're going to take the, actually the square root is gone, it canceled out, and I'm just left with 21 underneath there. And then I'm going to multiply that by vector b. Now remember that vector b has these three components. And to put this into simplest form and actually figure out where is this resultant projection vector, I'm going to multiply this scalar in and find the actual components. Remember, this would be like the point at the end of the vector. There we go. All right, so that's it for today's lesson. I just wanted to mention briefly that projections have a lot of applications. We're not going to look at any specifically in this class, but there are applications in engineering, quantum mechanics, computer animation, and other areas. Good luck with your homework.